as moderator for today's ARA Webinar Wednesday program entitled Electrically Conductive Concrete Heated Pavement Systems. Presenter, who I'll introduce a little bit later, is Dr. Hashem Abdullah. Next slide, please. I have a few housekeeping items I'll go over with you first of all, and then I'll be returning at the conclusion of the technical program to go through the Q&A with you. First of all, if you're having an issue with the version of the webinar, and you're connected with your computer speakers, then close the computer speakers and then call in on the phone. If you're still having a problem with the audio portion, or for that matter, the video portion, go to the chat, click on host, send the message to the host, and alert them that you're having a problem. They'll do their best to help you out. Next slide, please. At the conclusion of today's technical program, which will be approximately 40 minutes or so, we'll have about 15-minute Q&A program. We encourage you to ask questions during the entire technical program. We'll defer addressing those questions until the conclusion of the program. As you can see in slide number 3, we ask you to go to the top of your screen, go to the Q&A button, and type in your question. Direct the question and listen carefully. Please direct the question to the host and the panelists. This way we'll be able to facilitate your question. Next slide, please. To view the presentation in full screen mode, if you're not already there, just go to the drop-down arrow again at the center of your viewing screen, click on View, and click on the option Fit to Viewer, and you should be all set. Again, as I mentioned, I'll be returning at the conclusion of the program to go through the Q&A. Next slide, please. Now, finally, it's my pleasure to introduce my colleague and friend, Dr. Hashem Abdullah. He has a master's degree from the University of Colorado, a PhD from Iowa State, and during his time at Iowa State, both in achieving his doctoral program as a postdoc, he specialized in the topic that we'll be speaking about today. His overall expertise and experience extends beyond the topic of today to include rigid pavement design and performance evaluation. He's fairly knowledgeable as well in construction materials and forensic studies related to that topic. And then finally, we'll hear quite a bit about today, heated pavement systems and numerical models associated with that. So with that, I'd like to turn the program over to my good friend Hashem, who'll guide us through the details of this.
Yep. Thank you, Jerry. Welcome, everybody. This study was part of my PhD at Iowa State University and was funded by Federal Aviation Administration. So the ultimate goal of the project to eliminate the use of deicing chemical agent and provide or achieve accessible, open, and safe airports during winter events. So here is my outline for today's presentation. I will talk about the motivation of the study, and I will focus more about the design, construction, and performance of the full-scale electrically conductive concrete heated pavement system at Des Moines International Airport. And I will briefly talk about the conceptual design for electrically conductive concrete using different construction techniques, such as precast concrete or two-loft paving. And I will briefly highlight a number of benefits. So I just want to mention that I'm going to use ECON stand for electrically conductive concrete for the rest of my presentation. So what was the motivation? So as you can see, the presence of ice and snow on accumulation on paved surface can cause incidents and accidents, and also can cause significant delay and significant delays for the airplanes. And this is an example of airplane that skid off the runway at Chicago at Midway Airport and caused like a death of 6 years old. So traditionally we can use de-icing chemical agent and large snow plows to mitigate this problem. However, these methods are labor intensive and are not the most environmental solution to use. And also, as I mentioned, this study was funded by FAA, but also we can implement the ECON system for bridges. It's a good application also for bridges, so we can eliminate all of the accidents due to the presence of ice and snow. And also we can eliminate the corrosion, because typically we apply de-icing chemical agent on the bridges, and all of that chemical penetrate through shrink cracking, and when touch the steel and corrosion start, and then cause delamination and will significantly reduce the life of the bridges. So we're trying to eliminate all of these accidents, and also to provide extend the surface life for bridges by implementing this technology. So heated pavement system are an alternative promising approach that we can use, and typically categorized in 3 types: hydronic heated pavement system, electrically heated cable system, and electrically conductive concrete. Hydronic heated pavement system is a mature technology and works by embedding a pipe within the concrete, and then we circulate hot fluid, and then heat is released to melt ice and snow. Electrically heating cable, it's the same concept, but we embedded electrical wire, and then we connect it to the power supply to generate heat, and heat is generated due to the resistance of the heating cable. And the last type is electrically conductive concrete. As I mentioned, I will use ECON for the rest of my presentation. And this works by adding conductive material to the normal concrete to improve its conductivity. And then we place electrodes to allow electrical current pass through the material, and then heat generate. We will talk more about it in detail. And the rest of my presentation is going to focus only on the ECON system. So before we dive in the ECON system, here's an example of hydronic heated pavement system that was built in Norway. And this is actually the good location, because they built it in very congested area, and this is a very critical area. It's very difficult to remove ice and snow from this congested area. So that will provide safety for the crew to refuel the airplane, to load and unload in a safe manner. So we installed the ECON system at Des Moines International Airport, and this shows the overall sites. And here's another Google image that I captured before they start removing all of the existing slab. The slab were in poor condition, so they decided to remove all the existing slab, and then we found it a good advantage to implement the ECON system. So we selected only 2 steps to understand the performance of the system in a real airport environment. So we had multiple meetings with airport managers and staff to explain or to address all the challenges that we might face during the construction. So we provided them with all details with design and construction procedure. We had multiple visits at the site as well. So this kind of meeting was very successful and actually leads to a successful implementation. So you had to meet in advance to address all of the challenges. So the main component of ECON heat pavement system are power supply, electrical wire, PVC conduits, and electrodes. Electrodes are embedded in the ECON layer, and the bottom layer is a normal concrete. So typically we divided the whole thickness to 2 layers. The top layer is the ECON layer, and the bottom layer is the normal concrete. Since we only need to warm the surface, so we only construct a thin layer, about maybe 3 inches. And then we embedded electrodes at that layer, then we connected to the power supply. Then heat is generated due to the resistance of the material. So we will go through the design and construction as well. This is give you a overall of the main component of the ECON system. So this is the cross section that we use. This is the actual cross section. And as I mentioned, we constructed just a thin ECON layer, and the remaining is just normal concrete to save on construction cost. So the thickness was 3.5 inches, and we placed 2 electrodes. So the distance between electrodes, we determined that based on the energy required. And this is how it looks. This is just a 3D image, and we placed like 6 electrodes are highlighted in red, and then we connected them to the power supply inside the hangars. And since this was the first implementation, we heavily instrumented these 2 slabs with different sensors. So I tried to visualize them with a 3D image. So these like strain gauge, temperature sensor, moisture sensor. We extract all the data in order to understand the performance of the system and calculate the operation cost. So the actual electrode, these the actual electrode that we place in Des Moines International Airport, and this is a zoomed picture how we connected the electrode with the power supply. This is the power panel, and the electrician from Des Moines Airport helped us to connect or to do all of the electrical works. And we place, this is just a zoomed picture from the power panel, shows the electrical current monitor. We monitor the electric current, voltage, and power supply. So we use many sensors to extract all the data related to electricity, so we can understand how much that we are consuming for each slab. So the main difference between ECON mixture and the normal concrete is by adding carbon fiber. We add carbon fiber 1% by volume. The reason we add carbon fiber to improve the conductivity of the material, so we can allow electrical current go through the system, then heat generate. If you have a normal concrete, you will not be able to achieve heat generation. So we have to add carbon fiber in order to increase the conductivity, which is the reciprocal of electrical resistivity. So also we need to lower the electrical resistivity. So the good value that we see on the electrical resistivity for the ECON system, it should be like below 1000 ohm centimeter to provide you sufficient heat generation. Normal concrete, the electric resistivity is very high, so you will not achieve any heat generation if you connect it to the power supply. So I want to mention that the main property that you can distinguish between ECON mix or normal concrete is electrical resistivity. So we are trying to achieve low electric resistivity by adding conductive material, and in this study we use carbon fiber. And this shows the steps how to design the system. So first you have to identify where you want to construct the system. So this is a map, shows you the energy density for each state. This is just an estimate and give you a good idea about how much energy that you need in order to melt ice and snow efficiently. And of course, there's many factors that you can take in consideration, including, for example, the wind speed, how many inches of snow that you get every year, ambient temperature. So you have to take all of that in consideration in order to come up with the energy density that you want for melting ice and snow. And this is a reference for This map was taken from this reference, and you can see all of the details. And they will provide you with the heat transfer equations, use conduction, convection, and so on, if you wanted to specifically come up with the energy density for a specific location. So after you get that value, typically the energy density between 300 to 400 watt per square yard. So we developed this flow chart, shows you a step-by-step to design the system. So first, when you define the energy that you need, let's say 300 watt per square yard, this energy will prevent snow and ice accumulation on the paved surface. So it's site dependent. So after you define the energy, you select your slab side, typically 15 by 12 feet, and then you identify the electrode spacing, and then adjust your electrical resistivity value, and then you have to see the amount of power that you have. Based on that, you can come up with the sufficient design. If you cannot meet this design, you have different options here. You can change the spacing between electrodes, you can change the property of the material, and so on, until you achieve a good design that meets your expectation to prevent ice and snow accumulation on the paved surface. So this is another way to design the system. We can use a 3D finite element model. You can use the flow chart step by step, or you can use finite element model. It's not necessary to use finite element model, but it's a good tool out there. You can use it. So this shows the results of just an example results from the slab. So instead of you build a slab in the laboratory environment, you can build it with the finite element model. It will not take you a lot of effort and mixing the concrete and so on. It's very efficient and quick way to design. So this is the slab, this is 2 electrodes connected to the power supply, and this is just an example plot between the temperature and the time. For example, if you have an ambient temperature like below freezing point, about 10 Fahrenheit, how long is going to take you to reach about freezing point? The reason why we need to reach above the freezing point in order to melt ice and snow. When snow and ice hit the econ slab or econ surface, melt right away. So if you have like spacing between electrodes, 5 feet, 8 feet, 15 feet. So for example, with 15 feet, you will not be able to achieve good heat generation. So you can play with all of these parameters to come up with a sufficient and good design. So here's how the contractor lifted for us the 2 slabs. So this is, they built the normal concrete, and this is the 2 slabs that were dedicated for the econ demonstration. So first, they put the normal concrete at the surface. As I mentioned, just we put the normal concrete to save in construction material. And since we don't want to heat the whole system, we don't want to heat the whole thickness. So we put 4 inches or 4.5 inches thick normal concrete, and then we try to create a rough surface to ensure the bond between the normal concrete and the econ layer, because later on we're going to put the econ layer on top of the normal concrete. So we did that in 2 stages. We put normal concrete, and then we put the econ layer. So before we put the econ layer, the final layer, we have to place all the electrodes. So this is how it looks after we put the first layer, and these actual electrode at the side, and all of the red wires, and all of these are sensor. So we heavily instrumented with the strain gauge, moisture sensor to just understand the performance of the system. But if we need to build it again, we will not use all of that heavy sensors. We just use 1 or 2 temperature sensors just to monitor the temperature increase over time. And here, there's guys from electrician from Des Moines, and they connected all the electrode to the power supply inside. So they work in connecting all the power supply, and the ECON slab were next to the hangar. So we have existing power supply that we use it. We did not modify it. We just connect to the power supply, install the sensor for electrical voltage to determine how many energy that we draw from each system. So this is the normal. This is the ECON layer. So it looks like a normal concrete. We didn't have a specific equipment to place the ECON layer. So it's like normal concrete. We place on top of the ECON layer, and here's the electrodes out there. And then, like normal concrete, we have to cure the surface to prevent any shrink cracking and maintain moisture within the ECON layer. So this shows a very simple control system that you can use in order to turn the system on and off. For example, based on the sensor, based on the temperature sensor, you set up the temperature sensor that you want. As I mentioned, we just need to keep it above the freezing point. So if you have the temperature, surface temperature of 42, you will be able to prevent ice and snow accumulation. And the good thing about this system, you can connect it to the smartphone. And you can install the app, and then you can just, in a click of a button, you can turn the system on. You can turn the system off. You don't need any equipment, de-icing chemical agent, or large snow plows. It's a very efficient way to turn the system, even from your smartphone. So this is the first performance. It was this one was in December 2016. We had about 1.5 inches snow accumulation. So we turned the system in advance. I think about an hour in advance. And as you can see, snow accumulated on all of that slab except for the ECON slab. So when we turn the system on, you can see this is the thermal image. This is thermal image, shows you the heat distribution. So you see the red area, this is the ECON system. And you can see the temperature. We just needed to achieve like 2 Celsius, which is equivalent to maybe I think 42 Fahrenheit. So just to maintain the surface above freezing point. And we also tested during the night all the time. We did not, I guess, miss any snow events. So we tried to test it as much as we can, so we can extract all the good data and how the system works. So this picture shows if you have the heated pavement system, you don't need the largest snow plows. I was there at that time, and there are like 6 or 7 very huge snow plows. And if you have this system, you don't need all of these devices. Especially, I'm talking about especially congested area at gates. But for runways, we believe that it's easier to clean the ice and snow from runways because it's a very large area and open. But for congested area like gates, it's very difficult to use these large equipment. And if you use a small equipment, it will take you longer time to clean the ice and snow. And actually, some area in the airport, you have to, based on the FAA regulation, you have to clean ice and snow within 30 minutes. So you cannot leave the snow and ice accumulated more than 30 minutes in some critical area. So this is also the performance for the second year. You see the slab is working just fine. We're able to melt ice and snow. And here, this is a nice picture, shows all of the snow cover, all the slabs except for the heated pavement system. And this is why the snow falls. So one thing I noticed that when the snow falls and touch the surface, it's like a melt right away. So the efficient way to just turn the system in advance, like an hour in advance, you see the weather event if you have a snow. And if you wanted to keep the snow accumulate on the surface, then you turn the system on. It's going to take longer time, and we don't recommend that way. Unless this is not an important area, yeah, you can use this operation. So this is just shows a thermal image of it's like a time lapse. The purpose of this one to see the heat generation, how heat distributed over the entire step. So this is the first image before the heat starts. You can see the heat generation start in this area, and the temperature is still below freezing point. And then as you go from this picture to the right, you see the area start to becomes more red, and the distribution of the heat is more uniform. So the goal of this image to show that we can achieve uniform heat distribution on the surface. And you can reach, you see, 2.2 Celsius, equivalent to 40. And after this value, you can turn the system off. So you only need to turn it on and off during the winter events to prevent the snow and ice accumulation. So from the sensor that we instrumented, as I mentioned, current sensor, temperature, moisture, strain gauge, but this is just an example. Shows the temperature increase, over time, and the amount of current here over time. And this is just the time. So the operation. So I remember that. So we open the system before the snow falls an hour. And then the snow lasted for about 7 hours. You see that temperature increase over time, and the red line is the amount of current withdrawn from the system. And we place the sensor at different depths, 2 in econ layer and 1 in the normal concrete. Actually, we have also in the sub-base and sub-grade, just to see how heat goes. But typically heat usually goes to the surface layer to prevent ice and snow accumulation. So from this figure, we were able to calculate the operation cost. So if you are wondering about how much is going to cost you for the operation cost, so from the sensor that we instrumented, we extract all the data, and finally we come up with the power that you need for each slab. And the size of the slab at 15 by 13 feet. So you need about 5,800 watt for each slab. And if you wanted to divide it by the area, it's about 280 watt per square yard. This is equivalent to, for example, 3 light bulbs. If I try to make it easier to visualize the 280 watt per square yard. So it's equivalent to 3 light bulbs. So it's like you are consuming electricity for 3 light bulbs. This is how much the operation cost is gonna need in order to heat only 1 square yard. For 1 slab, it's equivalent to like 2 dryers. One of them consuming 3,000 watt. So a total of 6,000 watt per slab. And the size of the slab, 15 by 13 feet. And as I mentioned, one of the snow event stayed for 7 hours. So we ran the system for 7 hours. And if you want to calculate the cost for that duration for the 7 hours, is going to be about 19 cents per square yard. Based on the electricity cost is 0.08 kilowatt hour. This is electricity cost at Iowa State. And the construction cost for this system is about 50% higher than the normal concrete. We had many snow events at Iowa State, and we documented all of them, and this is just a few of the snow events that we had. to understand at which temperature that we can use the system, and we're able to melt snow and ice with all of these temperatures, for example, 25 below freezing point, even -11 Fahrenheit. So the system was very efficient in melting ice and snow with different air temperature and wind speed. We documented the amount of the thickness of snow that we were able to melt, and power supply for each case. So if you want to normalize the cost, we come up with the normalized cost, you want to say about 2.7, 2.8 cents per square yard per hour. This is like a normalized cost from all of that event, regardless of the air temperature, how long that we turn on the system. So let's say if you want to construct the system for a gate area in the airport, and the area is about 3,000 square yard, it's equivalent to 2,500 meters square. So at Iowa State, the energy cost is about 0.08 kilowatt per hour. So if you wanted to keep the system on for 1 hour, it's going to cost you about $80. And one snow event at Iowa, based on Iowa condition, lasted for 6 hours. So if you keep the system for 6 hours, it's going to cost you $500. And so we have all the snow events that occurred during 2016, 17. We recorded all of that. And for Iowa, typically they have, for example, they have like a 30 snow events. So if you have 30 snow events and each event snow lasted for 6 hours, you will be talking about 15,000. It's going to cost you the operation cost, 15,000, to prevent ice and snow. And they believe this is very cost-effective approach to actually prevent ice and snow accumulation. And the best way to operate the system, as I mentioned, just to turn the system in advance, to warm it up before the snow starts. So if you compare the normal concrete with the ECON system in terms of mechanical property or durability. So ECON provides better mechanical property and better durability, since we use fiber and we eliminate the use of harmful de-icing chemical agents. So typically fibers will reduce plastic shrinkage, drying shrinkage, and definitely will improve the strength of the material, and will keep the cracks tied together. And in terms of durability, since we are eliminating de-icing chemical agents, and this is good for also bridges. When you eliminate the application of de-icing chemical agents on bridges, it's gonna not save you like the incidents and accidents from the ice and snow accumulation, but also will improve the durability, will extend the surface life of the bridges, because also it will eliminate the corrosion. One of the big issue, I believe, for bridges is corrosion of the reinforcement. Since bridges is heavily reinforced, so when the de-icing chemical touch the reinforcement, corrosion will start, and you will have delaminations, and the surface life of bridges will significantly reduce. So this is the good thing about the ECON system, can be implemented also for the bridge application. So in terms of heat generation, we only focus on we focus more on the electrical conductivity, which is the reciprocal of electrical resistivity. So when you design and build it, we try to achieve good resistivity value. As I mentioned, below 1,000 ohm centimeter, to provide you with sufficient heat and to allow electrical current pass through the system. And also to ensure good bond between electrodes and the ECON material, because this is the link between the power supply and the ECON conductive material, electrodes. So we have to ensure good bond between electrodes and ECON system. So in terms of maintenance, we can follow the same maintenance practices for normal concrete, but the only difference, we can use conductive material to patch or fill the cracks. And there are possible material that we can use or develop, such as conductive asphalt or conductive mortar, depends on the situation. If you have a small crack, we can use conductive asphalt. So just to make uniform and heat distribution, if you use non-conductive material, may not heat that area. So if you have a large area that you need to fix, it's better to use conductive material. So you make it uniform and heat can generate in that area as well. So I will briefly mention about the conceptual design for bridges. If you want to apply for bridges, and let's assume you have only 2 lanes, so this is how electrode configuration is going to be laid out. So we put about, based on your design and the energy that you need, we put here 6 electrode per step. So this is how it's going to look. And also we connect all the electrode with the power supply through the PVC conduits. We use PVC conduits to house the electrical wire. This is more detailed sketch to show how we connect the electrodes, and this is a zoomed picture from the PVC conduits out here, shows all the electrical wire. But if anyone interested in implementing this for bridges, we can develop more detailed design and construction guides for the bridge application. So, as you know, precast concrete is very good to accelerate the construction process and reduce the traffic time. So we can use precast technology for heated pavement as well. So basically we can modify the precast and we put just a top layer, just the ECON layer as I mentioned. We add electrodes and the bottom layer just a normal concrete. And actually we had many discussions with the manufacturer that produce precast concrete, and they were interested in implementing this technology. So I think using precast concrete, it's a great idea for area that requires the heated pavement system that needs to be done in a very quick time and with reduced traffic disruption. And there's another technique that we can use, the two-lift paving. I believe two-lift paving is more common in Europe countries. They use it more. But here we can use two-lift paving. We can use a slip-form paver to accelerate the construction process of the ECON system. So basically, the steps that's out there, you have 4 steps. It's like a normal concrete. It's like a normal construction practice. But the difference, we add electrodes here and we connect it to the wires. And then we add the thin layer, about 3 inches or 3.5 inches thick ECON layer. And also we had a discussion with one of the largest companies that manufacture the slip form paver, and they were interested to modify or adjust the slip form paver to automate the installation of the electrodes. So electrodes, we can automate them, and instead of placing them by hand, it's going to take longer time. So overall benefit, there are a number of benefits if we use this system. So of course, safety is one of the big benefits that we get out of this system. So we can, in terms of airports, we can eliminate airplanes skid off the runway, like the example that I mentioned at the Chicago Midway. One of the airplanes skid off the runway and caused a death of 6 years old. And also for bridge application, we can not only eliminate the incidents and accidents, but also extend the surface life by eliminating corrosion-related problems. And also, definitely, we're going to significantly reduce the amount of labor, and you don't have to worry about storage, huge amount of de-icing chemical agent and also large plows. And environmentally, since we are eliminating the use of de-icing chemical, because if you use de-icing chemical, you have to treat the contaminated snow before you release it. And also I mentioned that we can improve the durability of the concrete or pavement because we are eliminating the use of harmful de-icing chemical. With that, this is my presentation, and I will pass it to Jerry.
Okay, thank you, Hashem. Very interesting presentation as it's getting to be almost late spring and summer. It's hard to think of wintertime again, for me at least. So before we get into the Q&A program, as we always do, want to give everybody an advanced look at what's coming up. First of all, if you're new to the program, it's been ongoing for over 2 years now. If you want to register for any of these events, just keep an eye on your emails, and you can register at the ARA.com/webinar, as you see in this slide. 2 of the immediate programs coming up. First, on May 26th, we'll be talking about performance specifications specifically related to pavements. And then on June 30th, we'll be sticking with the pavement theme. And as you recall, those of you who have been with us for a while know that we try to mix up the topics as best we can. So on June 30th, we're going to talk about pavement management for our good friends at the United States Forest Service. And we automatically think of high-tide arterials or interstate roadways, national highway system. But the U.S. Forest Service and related organizations have massive roadway systems where pavement management has to be applied as well. So in addition to that, we've got topics and presenters booked through February of 2022. So stay tuned. You'll be hearing all of our presenters, by the way, are ARA subject matter experts. Next slide, please. So I'd like to get into the Q&A program, and we do have a number of questions. If we do run out of time during the Q&A program, you can reach out to Hashem with questions that you might not have thought of during the actual program at his email address that you see listed here. So first question comes from Lydia, and she'd like to know if ECON can be powered by solar panels, and if you could at least estimate what the size of the solar panel system would be relative to a particular area. I guess that'd be a tough one, the second half of that.
Right, I agree. Yeah. Actually, the solar panel is a promising technology, and it's really great. And definitely, we can incorporate that to the system, and we can use solar panel. But in terms of the amount that we can use, it depends on the site. As I mentioned, we need approximately 300 watt or 350 watt per square yard. I think based on this number, you can estimate how much we can get from the solar system. Yeah.
Okay. You handle that well. I would have had a hard time trying to come up with that estimate as well. So we've got a question from John, and the next question is, how large of a surface can you heat? And I think it's referring to a single unit. And how big of an area can a single power supply unit kind of effectively manage?
So all of that, the area we can heat as much as we can, but all of that relies on the power supply. If we have a large power supply, we can heat many slabs. But as an example, if let's say if you have about like 800 amp, we can heat, I think, maybe about 15 slabs with the amount of current that I just gave, like about 800 amp. This is just an example. Yeah.
Okay. And,
yeah.
I have a question from Mary, and this is, you talked a little bit about pavements and the test application. Question is, can you construct ECON using concrete overlay technology?
Yes. Yeah, actually, we are using a two-lift approach, and we can use a concrete overlay for existing pavement. Let's say if you have an existing pavement and you wanted to install the system, we don't have to remove the existing pavement. We just put a thin layer on top of that, and we can use we can follow the concrete overlay practices, and also we add all the electrical component. Yeah, but concrete overlay definitely is a good option.
Okay. So the next question is, to what ambient temperature is it effective to melt existing ice and snow?
Yeah. So based on our experience on Des Moines International Airport, we were able to melt it all the way to minus 15 Fahrenheit. So I believe with this temperature, or minus 15, minus 20 Fahrenheit, we will be able to melt ice and snow. But yeah, it may take longer time because it's very cold temperature. But if you have like 10 Fahrenheit, it's gonna heat faster. So, but we will be able to melt within minus 15 Fahrenheit.
Okay. So I've got another question from Dan, and his question is there any need to provide for melted snow/ice drainage, especially in a larger area system?
Yeah, this is a good question, yeah. We can provide a drainage system, but the best way to operate the system is to open the system in advance before snow starts. When you open the system, like let's say an hour in advance, you can prevent all of the snow and ice accumulation. So you don't have any water or melted snow that you need to get rid of it. But if you keep the snow accumulate, then you turn the system on, we may come up with a drainage system, like a heated drainage system, in order to allow the flow of the melted snow. Yeah, but the best way to prevent it, just turn the system in advance.
Okay. All right. We have a question from Jerry. You addressed this topic during the presentation, but maybe you can elaborate on it. And the question is from Jerry: Can we automate the process of placing the electrodes?
Yes, because as I mentioned, we had a meeting with one of the largest slip form machines company, and they were interested in helping us to come up with the slip form paver to automate the process of the electrode installation. So we have many discussion with I remember the company is Gomeco. This is the paving manufacturers, and they were interested. So if there's a need, I think we will be able to come up with a solution to automate the process of installing the electrodes and any component related to the ECON system.
Okay, and the last question, at least as far as I see right now, is, and this is an interesting question, is will ECON create a radio frequency interference in an airport application?
Yeah, so we test that through our collaboration with the electrical engineering at Iowa State University, and we were able to see that there's any effect between the frequency interference with the airport, because the frequency of the communication is very high, and when we measure the frequency of the ECON, it's very small. So there's definitely no effect on the communications.
Okay, I don't have any other questions, but I want to remind everybody, it's often difficult to watch a presentation, at least listen to the presenter and formulate a question. So Hashem has been gracious and be receptive to addressing any questions you might send to his email address within the next 24 hours specifically on this topic. So with that, could we have the next slide, please?
Sure.
So just a few more slides, some details and logistics is all participants joining for the full hour of presentation will receive a PDH certificate and a PDF copy of the presentation, and allow us about 2 weeks to receive your certificate. And if you have any questions regarding either the presentation or your certificate, is just send it to the ARA webinar Wednesday address. Our policy relative to granting a PDH certificates follows the licensing boards of the respective engineering boards that exist around the United States. So that's not our policy, it's their policy. Next slide, please. And final slide for today. First of all, I want to thank everybody again for joining us. Great presentation, Hashem. And ARA is a great company. We're over 1,500 employees. One of our mottos is science and engineering for fun and profit. And we always strive to hire the most valuable colleagues. We're all inclusive as a family and an organization. We have a number of exciting opportunities throughout the United States, approximately about 40 offices. And if you're interested in the current employment opportunities, we have, again, one last web address for you to contact us, and just send us a brief description of your bio, and then as appropriate, we'll be in contact with you. So thank you all again. Have a blessed day, and we'll see you next month. Remember, the last week of May for performance-based specifications.